The black hole in the movie Interstellar is a colossal 100 million times the mass of the Sun, aptly named Gargantua. Yet even Gargantua pales in comparison to the true giant TON 618, which is a staggering 60 billion times the mass of the Sun. Black holes are more mind-blowing than you can imagine, and in this video, I'll break down everything you need to know about them. Hello and welcome to our channel Beyond Earth, your portal to the cosmos. The concept of black holes dates back to the 18th century, but it was Carl Schwarzschild who provided the first modern solution to Einstein's field equations of general relativity, describing what we now call a black hole. Later, scientists like John Wheeler popularized the term black hole in the 1960s. So, what exactly is a black hole? In simple terms, a black hole is a region in space where the gravitational pull is so strong that nothing, not even light, can escape from it. But how do these cosmic giants form? Black holes are born from the remnants of massive stars that have ended their life cycles. When a star that is at least 20 times more massive than our Sun exhausts its nuclear fuel, it undergoes a catastrophic collapse, leading to a supernova explosion. The core that's left behind continues to collapse under its own gravity, forming a singularity, a point of infinite density, and thus a black hole is born. This process is so intense that it warps space and time around it. Near a black hole, gravity is so intense that it can stretch and squeeze time, making hours feel like minutes and vice versa. In the movie Interstellar, we saw this firsthand. On Miller's planet, every hour equates to 7 years on Earth. The boundary surrounding a black hole is called the event horizon. It's the point of no return. Once anything crosses this boundary, it gets pulled into the black hole and can never escape. But what lies beyond the event horizon? That's a mystery that even the greatest minds in science are still trying to unravel. Some theories suggest that a black hole's singularity is a point in the future where all paths in space-time end. This is similar to the Big Bang, which is a point in the past where everything in the universe started. The main difference is that the Big Bang is a starting point in the past, while a black hole's singularity is an endpoint in the future. According to Stephen Hawking, black holes can emit radiation, now known as Hawking radiation, which causes them to lose mass over time. Eventually, they could evaporate completely, but this process would take longer than the current age of the universe for most black holes. While black holes and wormholes are both fascinating concepts in theoretical physics, they are not the same. A wormhole is a hypothetical tunnel connecting two separate points in space-time, potentially allowing for faster-than-light travel. There's no observational evidence that black holes are wormholes, but the idea remains a popular topic in science fiction. It's estimated that our Milky Way galaxy alone contains millions of stellar-mass black holes. Across the observable universe, there could be billions or even trillions of black holes, ranging from stellar mass to supermassive ones. Black holes themselves are invisible because they don't emit light. However, we can observe the effects of their immense gravity on nearby matter. The first ever image of a black hole's event horizon was captured in 2019 by the Event Horizon Telescope, showing a bright ring of light surrounding a dark shadow. There are three main types of black holes: stellar mass black holes, which form from collapsing stars; supermassive black holes, found at the centers of galaxies; and intermediate mass black holes, which are less common and bridge the gap between the other two types. There's also the hypothetical primordial black holes, which might have formed in the early universe. Did you know that there's a supermassive black hole right at the heart of our galaxy? It's called Sagittarius A star, and it's about 4 million times more massive than our Sun. Imagine the gravitational pull it exerts. This black hole is relatively quiet, but occasionally it flares up as it consumes nearby matter. Black holes can also merge with each other, creating even more massive black holes. These collisions are so powerful that they send ripples through the fabric of space-time, known as gravitational waves. These waves were first detected in 2015, confirming a major prediction of Einstein's theory of general relativity. The detection of these waves has opened a new window into observing the universe. One of the most intriguing aspects of black holes is the information paradox. According to quantum mechanics, information about the physical state of objects that fall into a black hole should be preserved. However, general relativity suggests that this information is lost forever. This paradox has puzzled scientists for decades, and even the legendary Stephen Hawking spent much of his career trying to solve it. Hawking proposed that black holes might emit radiation, now known as Hawking radiation, which could eventually lead to their evaporation. Recent research in quantum thermodynamics suggests that black holes might not be what we thought. They should be viewed as dynamic systems, shedding light on their quantum thermodynamic properties. This study also extends these properties to extremely compact objects, potentially contributing to resolving the black hole information paradox and enriching our understanding of quantum gravity. These findings challenge our traditional views and could lead to new theories about the nature of space and time. If you found this video fascinating, make sure to give it a thumbs up and subscribe to the channel.